Okay, let's look at question 3 carefully. Let S be a set and let P of S be the set of subsets of S. Consider the set P of S with the set difference operation denoted by backslash. For each of the 4 group properties listed above, prove whether or not the set P of S with the set difference operation satisfies the property. All right, so we got 4 properties. We want to look at them one by one and see whether this set P of S with the set difference operation backslash is a group, or it satisfies these 4 properties. Okay. So note that in this problem S is not given explicitly. So to establish a group property, you need to prove in general, i.e. your proof should not employ a specific example of S. However, to disprove a property, you may use a specific counterexample, because if a property fails for a specific S, it cannot be true in general. And so what that's talking about is that if this P of S with backslash doesn't work, that's going to be easy, because you just give one example where it doesn't work. But if you want to show it works in general, you have to give a general proof and not just use a single example. All right? So let's consider the 4 properties. First property is closure. What does closure mean? Closure means that if we've got 2 things, then the operation is also there. So let's do this. So we'll do what I've been doing is a to prove. Now, it means given any 2 elements of my set. Now notice that the set I'm working with is P of S. Right? This operation is an operation on P of S, not on S. So sets within S are my group elements. Okay? Group elements are sets now, not elements of S, but subsets of S. Okay? So to prove closure, I need to show given, and usually you don't know it's set by capital letter. So given AB in P of S, then A backslash B is also in P of S. All right, so is it true that given any 2 A and B in P of S, then A backslash B is also in P of S? No, it's actually true, because here you're just saying if you take 2 sets, then A backslash B is also a set. Okay, so I can say this is true, or let's say it this way, by the definition of backslash. Okay, so the set difference of 2 subsets of S is also a subset of S. Okay. If you go back to the definition of backslash, it just says all the elements that are in A that are not in B, and that's a subset of S. Right? So that's really all you have to do to show closure. Right? Let's do identity. Okay. All right, so let's see what we need to prove. We'll say there exists an element E in P of S such that E backslash A equals A backslash E is equal to A for all A in P of S. Right? So that's what we want to prove. I can say to prove or disprove. Okay. Now remember, I want to emphasize this, that E is an element in P of S. It's not an element of S, it's an element of P of S. So this E is a set. Okay. All right, now let's see about proving or disproving. Now you can look at some examples and see, well, this doesn't seem to be working out. And you want to identify why it's not working out. So there's a number of ways to do this. One way to do this is to notice that E not A and A have no elements in common. Any element of A is not an element of E not A. So there's no way that A could be equal to E not A. Now I could write that in words. Let's see if we can figure out a good way to write that. All right, so let me write it like this. Here's the disproof. Okay. Given A in A, or let's say, well, in order to say that, we have to say that A is not empty, okay? So let's say, let A be a non-empty element of P of S. And then, and let A be an element of A. Okay. Then, by the definition of backslash, E not A, I should say A is not an element of E not A. So it is impossible for E not A to be equal to A. And therefore, no identity element can exist. All right? So that disproves identity. All right? Now, if you don't have any identity, you can't possibly have an inverse, because the inverse is an element that operates with another group element that gives the identity. So I can just say that there is no inverse because there's no identity. Okay. And I can just leave it at that. Okay. If you want to say a little bit more, I can say the definition of inverse requires the existence of an identity. Okay. All right, so finally we're with associative. And it's probably good to do an example. So let's see, let's figure out to prove. Okay. We want to show that, or to prove or disprove, A not B not C is equal to A not B not C. Right. So I think in this point it's best to just try to find an example. And usually to find an example, you want to find some example that has the simple sets. Now the simplest sets in this situation are empty set and the entire set. So see if you can form an example with empty set and entire set, and by thinking about it a little bit, you can say let A equal. Okay, so here's I'll say disprove. Let A equal B equal C equal S. Now this took a little bit of thought, but that's something you can try. Notice that when you take the not operation, it makes the set smaller. So in this case, you're knotting something that's small. So that's kind of why I thought about this, is that here, if you take B and C both to be equal to S, then S not S is the empty set, and you'll just get S back again. So in this case, then this here would be equal to S not S not S. Now what is S not S? S not S is the empty set. So how am I going to do empty set? Let me just do, so in fact it's the empty set not S which is equal to the empty set. And A not B not C is equal to S not S not S not S, which is equal to S not empty is equal to S. Okay, since the two are unequal, it follows that this is not associative. All right, so that's how we get our 4 parts for the 4 group properties of set minus, and definitely it does not give me a group. Okay.